This scene deals with the subject many fathers find so difficult.
Welcome to podcast V0.1, where we break down the latest research and tools for curious engineers. Today, we're diving into a really critical challenge in modern software systems, network security, specifically detecting anomalies. Think about it. We're dealing with everything from sophisticated intrusions into corporate IT networks, to stealthy hacks targeting critical systems like cars. Detecting these attacks quickly and accurately is paramount, but doing it across massive, distributed networks without leaking sensitive user data is a huge headache. Centralizing all that network traffic for analysis just isn't feasible or desirable from a privacy perspective anymore. So how do you build a smart detection system that learns from diverse, distributed sources while respecting privacy? That's exactly what a recent paper titled Network Anomaly Detection in Distributed Edge Computing Infrastructure tackles. The authors propose a fascinating approach combining the privacy benefits of federated learning with the sheer power and scalability of Apache Spark and Kubernetes to create a highly accurate, resilient detection system that learns collaboratively across edge devices. Let's set the stage a bit more. Traditional network anomaly detection systems often hit a wall when faced with the scale and complexity of today's distributed environments. Think edge computing, IoT deployments, connected vehicles. These networks generate enormous amounts of traffic data, often spread across geographically diverse locations. Trying to funnel all this data back to a central server for analysis creates bottlenecks, increases latency, and, crucially, raises significant privacy and security concerns. Imagine collecting detailed network logs from thousands or millions of user devices or sensors. That's a treasure trove of sensitive information you probably don't want sitting in one place. Furthermore, many traditional methods rely on predefined rules or signatures, which struggle to catch novel or zero-day attacks, the kind of subtle, previously unseen threats that are becoming increasingly common. Even machine learning approaches face challenges. Centralized ML requires that data concentration we want to avoid, and the sheer computational load of processing and analyzing petabytes of network traffic is immense. This problem gets even trickier in specialized domains like automotive networks. Modern cars are packed with electronic control units communicating over networks like the Controller Area Network, or CAN bus. These systems can be vulnerable to attacks like masquerade attacks, where malicious messages mimic legitimate ones to disrupt vehicle functions, perhaps subtly altering sensor readings or even interfering with braking. Detecting these stealthy attacks requires sophisticated analysis, often directly on or near the vehicle itself, where resources might be limited and data privacy is crucial. So the core problem is how to perform accurate, large-scale network anomaly detection across diverse, distributed systems without centralizing sensitive data, while also being robust enough for real-world deployment. This paper introduces a framework designed to hit all these points by cleverly integrating several key technologies. The heart of the solution is federated learning, or FLORIDA. If you're not familiar, FLORIDA is a machine learning technique where multiple clients, these could be edge devices, servers, sensors, even cars, collaboratively train a shared model without ever sending their raw private data to a central server. Instead, each client downloads the current global model, trains it locally on its own data for a short period, and then sends only the updated model parameters, like the weights and biases of a neural network, back to a central server. The server then aggregates these updates, typically by averaging them, using a method like federated averaging or FedAVG to produce an improved global model. This cycle repeats. The beauty is that the raw data never leaves the client device, preserving privacy. It's like different teams improving parts of a blueprint locally, and only sending summaries of their changes to the chief architect, who combines them, rather than everyone sending their entire detailed drawings back and forth. Now, FLORIDA on its own is powerful for privacy, but deploying it effectively in a large, dynamic environment with potentially thousands of clients requires robust infrastructure. That's where Apache Spark and Kubernetes come in. Think of them as the engine and the operating system for this distributed learning process. Apache Spark is a well-known distributed computing framework, optimized for large-scale data processing. Its ability to perform computations in memory makes it very efficient for the kind of iterative algorithms used in machine learning, speeding up tasks like pre-processing client data or handling model updates. Kubernetes, the container orchestration platform, provides the infrastructure layer. It manages the deployment, scaling, and resource allocation for the Florida clients and the global server, running them as containerized applications, likely using Docker containers. This makes the whole system scalable. You can easily add or remove clients or server resources, and manageable. The paper describes a cluster setup with a master node coordinating tasks and multiple worker nodes where Spark executors run inside Kubernetes pods, handling the distributed computations for the Florida clients. This integration allows the system to efficiently manage the computational workload across all the participating nodes. So we have Florida for privacy-preserving learning, Spark for efficient distributed processing, and Kubernetes for scalable orchestration. But there's one more crucial piece for real-world edge environments: fault tolerance. Edge devices can be unreliable. They might have intermittent network connectivity, limited battery life, or simply crash. If clients constantly drop out during training, it can derail the whole Florida process. Waiting for all clients to report back before updating the global model, like in basic Fed AVG, becomes impractical. This paper introduces a clever solution: an adaptive checkpointing mechanism. Checkpointing is like periodically saving your work. In this context, each client periodically saves the current state of its local model and optimizer during its local training phase. If a client fails or disconnects, it doesn't have to start its training all over again when it comes back online. It can simply reload its last save state and continue. This significantly reduces the impact of failures. But when should clients save their state? Saving too often adds overhead and slows down training. Saving too infrequently means losing more progress if a failure occurs. The authors tackle this trade-off using a statistical approach. They model the probability of client failure using the Weibull distribution, a model often used in reliability engineering that can capture failure rates that change over time. Based on historical failure data, which gives them the parameters for the Weibull model, they calculate the optimal checkpointing interval, the frequency that minimizes the total expected time lost due to both saving checkpoints and recovering from failures. It's a neat bit of applied statistics to make the distributed system more robust against the inevitable hiccups of the real world. The recovery protocol is designed to handle failures gracefully. If a client fails, it tries to restore from its latest checkpoint. If a checkpoint isn't available, it can be reinitialized with the latest global model weights. Even if a failure happens during the aggregation step on the server can either wait for recovery or potentially redistribute the failed client's workload, ensuring the overall training process continues. Alright, that's the architecture. Florida with Spark and Kubernetes, plus adaptive Weibull-based checkpointing. Does it actually work? The authors evaluated their framework extensively, using two distinct and challenging datasets. The first is UNSWNB15, a widely used benchmark dataset for general network intrusion detection. It contains a mix of normal traffic and various modern attack types, like exploits, fuzzers, denial of service, reconnaissance, backdoors, and shellcode. The second dataset is ROAD, the Real ORNL Automotive Dynamometer dataset. This one is particularly interesting because it contains controller area network, CAN bus, data recorded from a real vehicle, including realistic, physically verified masquerade attacks designed to interfere with vehicle systems. Using both datasets allows the authors to demonstrate their framework's effectiveness not just for general IT security, but also for specialized, critical infrastructure like automotive networks. For the machine learning model itself, they used a deep neural network designed for binary classification, normal versus anomaly. It takes process network traffic features as input and uses a series of dense layers with 1024 down to 32 neurons and ReLU activations, along with techniques like batch normalization for stability and dropout to prevent overfitting, ultimately outputting an anomaly probability via a sigmoid function. The results are quite impressive. On the UNSWNB15 dataset, their proposed method achieved an accuracy of 97.5% and an AUCROC score of 0.96. AUCROC, or Area Under the Receiver Operating Characteristic Curve, is a good metric here because it measures how well the model can distinguish between normal and anomalous traffic across different detection thresholds, which is especially useful when dealing with potentially imbalanced data where anomalies might be rare. On the automotive road dataset, focusing on detecting masquerade attacks, they achieved 91.4% accuracy and an AUCROC of 0.89. These results significantly outperform the baseline methods they compared against. One baseline was standard federated averaging, FedAVG. The other was FedL2P, and Florida approach that uses meta-learning techniques to help personalize models for clients with diverse data. On UNSWNB15, FedAVG reached only about 89% accuracy and FedL2P about 92%. On road, the gap was similar, with FedAVG at 85% and FedL2P at 89%. So the proposed integrated framework clearly provides a substantial boost in detection performance. Not only that, but it was also faster. The training time on UNSWNB15 was 300 seconds for their method, compared to 600 seconds for FedAVG and 550 for FedL2P. Similarly, on road, it took 430 seconds versus 720 and 670 for the baselines. This efficiency likely comes from the optimized distributed processing using Spark and the potentially smoother convergence enabled by their aggregation approach. The authors also backed up these performance differences using statistical significance tests, specifically the Mann-Whitney-U and Kolmogorov-Smirnov tests, showing that the improvements weren't just random fluctuations but statistically meaningful, with p-values well below 0.05. Beyond raw accuracy, the paper looked at scalability and fault tolerance, key concerns for any software engineer building distributed systems. How does the system perform as you add more clients? The results show that while accuracy naturally tends to plateau or slightly decrease as the number of clients grows very large, likely due to increased communication overhead and aggregation complexity, their proposed method consistently maintained higher accuracy than the baselines across different numbers of clients. This suggests the architecture handles scaling better. What about when clients drop out? They simulated different dropout rates. Again, their method showed greater resilience. Its accuracy degraded more gracefully compared to FedAVG and FedL2P as the dropout rate increased. This directly validates the effectiveness of that adaptive checkpointing mechanism we talked about. By allowing clients to recover quickly from failures, the system maintains high performance even in unreliable environments. So what's the big picture here for us as engineers? Why should we care about this work? Firstly, it directly addresses the critical tension between needing comprehensive data for effective security monitoring and the imperative to protect user privacy. Federated Learning offers a viable path forward, and this paper shows how to make it practical at scale for network security. Secondly, the integration with Spark and Kubernetes is key. It turns Florida from a potentially academic concept into something deployable on realistic, large-scale edge infrastructure. Engineers working with distributed systems, microservices, or cloud-native architectures will recognize the importance of using tools like Kubernetes for managing complexity and Spark for handling heavy data lifting. This framework provides a blueprint for how these pieces can fit together for privacy-preserving distributed ML. Thirdly, the focus on fault tolerance via adaptive checkpointing is a nod to real-world engineering realities. Distributed systems, especially at the edge, are messy. Things fail. Having a built-in, statistically optimized mechanism to handle these failures makes the system far more practical and reliable than simpler approaches. The application to the automotive road dataset is also a significant highlight. It demonstrates the framework's versatility beyond traditional IT networks and its potential for securing cyber-physical systems and critical infrastructure where stealthy attacks can have serious physical consequences. This opens doors for applying similar techniques in other IoT domains, industrial control systems, or smart cities. Now, no system is perfect, and the paper acknowledges areas for future work and potential limitations. which implicitly touch on questions we might have. For instance, what about the communication overhead? While Florida avoids sending raw data, coordinating model updates and parameters across potentially thousands of clients, especially orchestrated by Spark and Kubernetes, still involves network traffic. The paper shows excellent overall performance, suggesting the overhead is well managed within their setup, but a deeper dive into the specific bandwidth usage versus accuracy trade-offs, especially under extreme scale, is noted as future work. How quickly can the adaptive checkpointing react to sudden changes in network stability? Since it relies on historical failure data to tune the Weibull parameters, a sudden shift in failure patterns might require some time for the system to gather new data and recalculate the optimal checkpointing interval. This adaptation speed could be a factor in highly dynamic environments. What about performance on extremely diverse or imbalanced data? The framework performed well on UNS WNB15 and ROAD, but the authors note that real-world IoT deployments can present even greater challenges with highly heterogeneous device types, data distributions, or extreme class imbalance, where anomalies are exceedingly rare. Adapting the framework for such scenarios might require further algorithmic refinements, perhaps in the aggregation strategy or local client training. Finally, what are the practical deployment hurdles? Integrating this requires managing a Kubernetes cluster, configuring Spark, and deploying the Florida components. Edge devices need sufficient resources to run their local training tasks and communicate effectively. While Florida aims to keep client-side work lighter than full centralized training, it's not zero cost. Integrating this into existing, potentially resource-constrained edge infrastructure would involve careful planning and system integration effort. In conclusion, this research presents a compelling framework for network anomaly detection in distributed edge environments. By integrating federated learning for privacy, Apache Spark for efficient processing, and Kubernetes for scalable orchestration, and adding a clever adaptive checkpointing mechanism for robustness, the authors have demonstrated a system that achieves high accuracy, efficiency, and resilience on both general and specialized network data. It's a significant step towards building practical, privacy-preserving security solutions for the increasingly complex and interconnected systems we rely on every day. It tackles the challenges of scale, privacy, and reliability head-on, offering a valuable blueprint for engineers looking to apply advanced machine learning techniques in real-world distributed settings.